Good afternoon, 2A, class of 2A. Today is November 21st? It's November 21st, I believe. We were supposed to have class today, but as you know, it was canceled due to the air quality. It's still pretty poor out there. Granted, it is raining outside now, so the air quality should definitely be increasing. I'm going to continue this online lecture just like I did for the previous two, so that you guys can be caught up with the material that we're supposed to go over. Unfortunately, all the material that you learn in 2A has a tendency to carry over to the next two classes, so we can't really skip anything, which is why I'm giving you these lectures. That being said, the first day of class on Monday, when we return from our Thanksgiving break, I'm going to review as much as I can in forms of examples so that we can get everybody back up to speed for those who missed the online lectures or did not watch them. I will try and be as accommodating as I can. There's just a lot of material to go over. Please send me emails if you have any questions. I'll try and hold extra office hours and such. Okay, so today we're going to talk about, our topics for today are magnetic properties, physical properties for elements on the periodic table. We're going to go over some Lewis structures, resonance structures. We have one resonance structure example. Some various covalent bonds and definitions. Some of this is going to look like a review, and dipoles. I don't have time to go over valence shell electron repulsion theory or VSEPR. The reason I don't want to do that here is because it's all about geometry. It's all about shapes. And seeing them in person and talking one-on-one will bring you to an understanding of how these shapes work, and there's a lot of shapes. So instead of teaching you that here online where it can be a little bit disconnected, I'd rather do that in person. So last lecture we talked about some periodic trends. So here I have a blank periodic table without the F block, where we're going to do a quick overview of how these periodic trends look on the table. And so first, let's draw two arrows, this direction, this direction. We use two different colors for this. So in this direction, heading towards fluorine, which is right here in this box, electronegativity increases, it's En. Our electron affinity increases. Our Z effective increases as such. So if we go from the bottom left to the top right, our electronegativity and electron affinity, the ability for atoms and elements to want electrons so they can get this noble gas configuration increases. And you'll see tables like this online or on textbooks. The textbook has a pretty good one. Conversely, in the opposite direction, I'm going to use the color green for this. If we go in this direction and this direction, so now we have that this way. It's a bad arrow. In the opposite direction, we have increasing radius. We have shielding, the ability for the core electrons to shield the valence electrons, which will affect how big the atom is going to be. And finally, metallic character. Metallic character. So elements at the very bottom left of the table are more metallic in character, meaning that they want to get rid of their electrons. They're very big and poofy. Their valence shell is so large that they want to get rid of their electrons. Or if we go in the opposite direction, when we get to fluorine, we find that the fluorine atom is very, 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 very tiny. It's very good at shielding, and its radius is very small. It is not metallic in character. It's nonmetals. We have nonmetals on this side. We have metals right here. And then of course we have the metalloids, which are somewhat metal and somewhat non-metal in character, but for the sake of simplicity, this is a basic example. Okay. That being said, let's move on to magnetic properties. There are several magnetic properties of electrons and magnetic fields. Here's a listing of a few examples. I am going to post these notes online later today when I post the online video, so you'll be able to print this out, you'll be able to write stuff on it as we move along, as we follow along in the lecture. Here's some listing of some examples we're going to go, you may be familiar with. We have ferromagnetism, antiferromagnetism, spin glass, paramagnetism, and diamagnetism. We will only cover these two, paramagnetism and diamagnetism. In future classes, you may go over these three and others, but for the sake of this general chemistry course, we're only going to go over paramagnetism and diamagnetism, and they're contrasting each other. They're very, very simple. So first, we have paramagnetism. It is the net magnetic moment caused by unpaired electrons. Having at least one unpaired electron results in paramagnetism. So when we do our orbital electron configuration, we have our upspin, we have our downspin. If we have any unpaired electrons that don't have a downspin electron with it, or they're not paired, it's going to show some magnetism. That would be paramagnetism. The way I always like to remember it is, if you have paramagnetism, they're always spinning in the same direction. So I like to think as parallel, paramagnetism, parallel. That's just a little idiom that I came up with myself to memorize this. In contrast, we have diamagnetism, in which all electrons in the atom or molecule are paired and there is hardly any magnetic effect. So it is the exact opposite of paramagnetism. And I have an example for you guys. Is chromium a paramagnetic or diamagnetic element? So we have chromium. Its electron configuration, its noble gas configuration, is argon. And let me see if I can find, let me pull the pure argon real quick. Yes. Let me use this handy dandy one. Zoom in on this. So argon is right here, chromium is this row. So we have 4s2, 3d, 1, 2, 3, 4, but chromium is an exception in that to get a half-filled d orbital, it promotes one of the s electrons to the d orbital. So in actuality, our electron configuration for chromium is 4s1, zoom out again, 3d5. So what I'm going to do is I'm going to draw the orbital electron configuration where we draw the boxes. Let's see, 4 lines. 1, 2, 3, 4, 5. So this is our 3d orbital. We'll put 4s1 over here. So we have 1 electron here and 5 electrons here. I'm going to, I probably should have written this over here. So it should have 2 in here, but we're going to put 1 in the d orbital. So we have 4s1, 3d5. We want to spread this out because of Hund's rule. 2, 3, 4, 5. So because all of these electrons are unpaired, this is a paramagnetic element. And later in the class, when we do molecular orbitals, that will be probably next week, if not the following week, the last week, you can also apply this idea to the orbitals that are created when 2 atoms come together to form a molecule. It's probably my favorite part of the course, to be honest. Right. Some other properties that you guys should know. Because metals have a low ionization energy, meaning it's easy to release an electron, they are more easily oxidized. So they lose an electron, they gain that positive charge, making them good reducing agents. In contrast, nonmetals are easily reduced, meaning they want to gain that electron. So they are good oxidizing agents. Metals, additionally, make good basic oxides, such as this example. We're going to use magnesium. as an example. So if we have magnesium oxide as a solid, we toss it in water, it's going to act as a base. This is liquid. It's going to make the basic magnesium hydroxide molecule. So magnesium has a charge of 2+, so it has to have 2 hydroxide molecules to balance out the charge. These metals make good bases because of this idea of low ionization energy. They make great good basic oxides. In contrast, nonmetals make good acidic oxides. But before we get to here, let's talk a little about the reason we call the alkali, the first 2 columns are called alkalis because of this idea that they make good bases. Conversely, nonmetals make great acidic oxides. So as an example, let's do a sulfur dioxide. This is a gas. It smells absolutely awful, and I do mean absolutely awful. If we were to bubble sulfur dioxide into a beaker of water, you form the oxyacid for that gas. So in this case, we would make sulfuric acid, H2SO4. Right. That's all the entire periodic trends section of the course. We are done with periodic table trends. But of course, as chemists, we're interested in bonding. We like to know how things are bonded with each other. So the rest of the course is going to be mostly talking about bond theory, various types of bonds, drawing molecules in a geometric shape, understanding things that follow such things as the octet rule, and such. So Lewis theory and bonding. Lewis theory is built on the idea that a noble gas configuration is desired. It is based on these following statements. When bonding, valence electrons are involved in bonding, not core electrons. So you remember from the previous class, not the review class, but the previous class before that, we talked about how we have the core electrons are nearest to the nucleus, and then the valence shell is the outermost subshell. That valence shell is what does all the bonding, not the core electrons, only the valence shell. Ionic bonds, which we talked about in like the second day of class, are the transfer of electrons between a metal and a non-metal. So you have something from the left side of the periodic table bond with something in the right side of the periodic table, or something from the transition metals bond with something on the right side. Covalent bonds are the sharing of electrons between 2 nonmetals. So that would be if we had nitrogen and nitrogen bond with itself, oxygen, oxygen, etc. And finally, the meat of it is the octet rule, or the noble gas configuration, which says that desired configurations of atoms where they are surrounded by 8 electrons. Having 8 electrons comes from the fact that they will have 2 s electrons and 6 p electrons during the filling of the off-bow principle. So if we go back to, where's my pointer? I want my pointer. I love my pointer. Yes. Zoom in on this thing. This is doesn't give you atomic whole lot of information, but you get the idea. This is a nice periodic rule that gives you like the history of some of these elements. So this idea of the octet rule comes from the fact that we have 2 s electrons, and adding 6 p electrons will give you this noble gas configuration. So you want to have 8 electrons around your atom in order for it to be happy. Later in the class, we're going to find out that this idea, you have molecules that obey the octet rule, and unfortunately you have molecules that do not obey the octet rule. For now, we're just going to talk about the ones that do obey it. So let's move on. So Lewis came up with Lewis symbols. This indicates valence electrons. The number of valence electrons is determined by the column number indicated by the Roman numeral followed by A on the periodic table. So if we go back to the periodic table that we had in the book, and we zoom in on this, you'll notice that some of these columns have, hopefully you can see that, that looks pretty clear. We have columns 1, 2, 3, 4, 5, all the way to 18. But below that, we have number 1A, 2A, and then we have this entire B section, which we're going to ignore. And we have this A section again. This number that's behind the A tells you how many valence electrons, using Lewis theory, this element has. So carbon has 4 electrons, nitrogen has 5. So you literally just go 1, 2, 3, 4, 5, 6, 7, 8. It's a very easy way to determine how many electrons the valence shell is going to have for that given element. And the way we like to write this down, I'll give you some examples. I'm going to change colors to purple. The purple marker is not fried. It's not fried. So let's zoom this out a little bit. Switch this up. So if I were to write the Lewis symbol for hydrogen, I write the atomic symbol for hydrogen, which is just an H. And if we look at the periodic table, it has the number 1A in front of it, so it only has 1 electron. So we just put a dot in front of it. Let's do something a little bit more complicated. Let's look at oxygen. Oxygen's atomic symbol is O. O is going to have 6 electrons around it. So we would go 1, 2, 3, 4, 5, 6. It doesn't matter what the order of this is, as long as you have 6 electrons around this symbol, and you don't write it in like this. So if you write 1, 2, 3, 4, 5, 6, this is incorrect. Don't write it in like that. The way I like to do is I like to go clockwise around, so 1, 2, 3, 4, 5, 6. That would be the correct answer. Let's do chlorine. Chlorine is a halogen. It is so close to having a noble gas configuration, so it's going to have 7 around it. 1, 2, 3, 4, 5, 6, 7. Like this. Beryllium. Beryllium is going to be, I'm just going to write it 1 and then 2 like this. You could write the other one here. Typically want to go around one circle before you start filling in pairs like you do for these. Argon. Ar. This one has a noble gas configuration because it is a noble gas. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8. This is a happy little atom that doesn't want to receive or give away electrons. And as such, the ionization energy for noble gases is typically really high because they're stable. They don't want to remove or gain an electron. Good. Let's see. Boron. B. Boron is right above aluminum on the periodic table. It's right before carbon. So we have 3. 1, 2, 3. So what you can do is you can make Lewis structures out of these. So these are Lewis symbols for individual atoms, or you can combine 2 atoms together to make a molecule. Lewis structures, or Lewis formulas, are a combination of Lewis symbols. Again, ionic bonds are bonds created when electrons are transferred from a metal to a nonmetal, and covalent bonds are formed when electrons are shared between 2 nonmetals. So I'm going to do an ionic bond between between a metal and a nonmetal, and a covalent bond between nonmetals. So as an example, let's do sodium chloride. Sodium has 1 electron like so. And then we're going to combine that with chlorine atom, which has 7 electrons around it. These 2 are going to create an ionic bond where the sodium atom is going to give away its electron to chlorine to form sodium chloride. 1, 2, 3, 4, 5, 6, 7, 8. Where we have, that should be an 8. We have, this is also represented by sodium being a cation, and chlorine being an anion. And that ionic attraction is what creates the bond. It's the attraction between a positive and a negative. So this is when a metal and a nonmetal. For two nonmetals, let's do hydrobromic acid. We're going to treat hydrogen as a nonmetal for this, not as a metal. Hydrogen has 1 electron. Bromine, again, like chlorine, is a halogen, so it has 7. 1, 2, 3, 4, 5, 6, 7. These two are going to come together, and they're going to share their electrons. So hydrogen isn't just going to simply give it to bromine, they're going to share their electrons. And the way we represent this sharing is by making these two dots a bond. They are sharing their electrons. This is between two nonmetals. All right. Let's go over various types of bonds. And some of these are going to be familiar because we're talking about ionic and covalent bonds again. So an ionic bond again, these are metal bonds to nonmetals by transferring electrons. The metal is going to give away its electrons, the nonmetal is going to accept them. They're going to have the noble gas configurations, they're going to be happy. Covalent bonds, again, these are non-metal bonds by sharing electrons. We have the coordinate covalent bond, which is a covalent bond where both electrons are contributed by one atom, often observed with oxygen. This concept is described in much higher detail in 2C. So for those who are taking Chem 2C, you guys are going to make metallic molecules in which the metal is surrounded by other atoms or other molecules, and those molecules like to coordinate towards the metal center. So as an example, let's do phosphate. Actually, let's use a blank piece of paper. We're gonna put the phosphorus in the center. It's our central atom. I'm gonna put 4 oxygens around it, and we're gonna go over in detail how to draw these later. 3, 4, 5, 6. And whenever you have a molecule that has a charge, such as phosphate, which has a 3- charge, you always draw in large brackets, put the charge up at the top right. Some professors also like to draw in just a corner like this and then put 3- instead of drawing the whole bracket. You'll especially see that if you take in organic chemistry. And so a coordinate covalent bond, this phosphorus atom is coordinating its electrons to this oxygen atom. I'm going to draw it right here. So I'm going to draw these 3 bonds. We're just going to ignore them. And what's happening here is the lone pair, these 2 electrons in the central phosphorus atom, are bonding to the 6 electrons to this oxygen. And that's what this coordination is. It's coordinating towards the oxygen. And you especially see this in, like I said, metals with oxygen, where the oxygen is giving its electrons towards the metal. It's coordinating towards it. Again, we have to write our brackets because it's charged. 3-. We probably won't be going into great detail for coordination covalent bonds in this class, simply because of the situation. And really there's not much to talk about them in this course until you get to 2C, where you're talking about metals bonding with ligands, as we like to call them. We also have, finally, we can talk about multiple bonds. Multiple bonds are covalent bonds that can form double or triple bonds, the sharing of more than 2 electrons. So let's do carbon monoxide here. Carbon has 4 electrons on its own. Oxygen has 6. And if we put these two together, we can form a double bond. I'm going to do 1, 2, 3, 4. And oxygen has 6. 1, 2, 3, 4, 5, 6. So the way we represent double bonds is when we form our bond, instead of putting 1 line, we put 2. Like so. Of course, the correct structure for carbon monoxide, we're going to get to this when we talk about the octet rule. This is not the correct structure. It would be to make a triple bond, because right now the octet rule states that every single atom has to have 8 electrons around it, which include the bonds. So right now our carbon has 1, 2, 3, 4, 5, 6 electrons around it. Our oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So our oxygen is happy, but our carbon isn't happy. So what we can do is we can move this lone pair down here to make a triple bond. So I'm going to do the Lewis dot structure first, and then I'm going to show the way we like to represent it in answers. 1, 2. So this is going to look weird. So these 6 electrons are being shared amongst the carbon atom and the oxygen atom. So to represent a triple bond, we would put 1, 2, 3. And there's 6 electrons in here. So now, I remember in the very, very beginning of the class, we talked about organic very, very, very briefly. We were only worried about these single bonds between the carbons and hydrogens. Now you can be presented with carbons that are bonded to other atoms with double bonds and triple bonds. And you can also expect the same thing for nitrogen, to have double bonds and such and such. And you may be asked a question like this on the final. I can do examples for this class, especially when we get to hybridization, which we're going to talk about later in the course. We also have polar covalent bonds. These are bonds where the electrons are not shared equally between 2 atoms because of differences in electronegativity. Polar means that there is a pole or a dipole because electrons are unequally distributed in the molecule. In contrast, the molecules can be, there's some missing over here, non-polar. I should say non-polar, sorry. An example of this, I have a polar molecule and a non-polar molecule. So the way we like to describe polar and non-polar molecules, and we're going to go over this again in 2B for those who are taking 2B when we're talking about interactions between molecules. A polar molecule would be such that we have an atom that is not as electronegativity, doesn't have an electronegativity that is higher than another atom. So here's hydrofluoric acid. Fluorine is a very, very electronegative element. It's the most electronegative element. It loves to take in that electron. And so when we talk about these polar bonds, we like to think of the electrons being kind of shared in a cloud. And so the way books like to describe them are with these cloud-shaped figures with colors ranging from blue to red, where red means there's more electrons over here than over here. So because fluorine is more electronegative than hydrogen, it's hogging most of the electrons, which gives it this red shade. So I'm going to draw an arrow with the back end like this. This says that it is polar in this direction because the electrons are more on the right side of this than on the left side. And the other way we like to describe this is using little delta minus, little delta plus. This means that on this side of the molecule, it has more electron density on the right side than it would have on the left side. So this is an example of a polar molecule. Dan is smirking back there, I don't know why.
Because electrons